Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, dear students. Welcome back to this TV learning series program. Teacher Patrick, I'll be with the Senior 5 Chemistry class. And we are going to look at unit number 7. This is our second lesson. And this lesson is about the physical properties and the acidity of these carboxylic acids. So I want to welcome you once again. Within this 30-minute session, we'll be together. Please pick your notebook and a pen so that you can note down some important information as we go along together. So in the previous lesson, we talked about the nomenclature. Mainly we're talking about the nomenclature and the isomerism of these carboxylic acids. So I just want to give you some few examples that can remind you of how these carboxylic acids are named. If you remember very well, we said that carboxylic acids are compounds, organic compounds that contain this group, which is a carboxyl group. We called it a carboxyl. This is carboxyl group. Whereby, in some cases, it can be written in this form, where this R may represent an alkyl group. It may represent an alkyl group. This R, either methyl, ethyl, butyl, isopropyl, and so on. Or it may represent a hydrogen atom. A hydrogen atom. So that is what we mentioned about in the introduction of these carboxylic acids. And then, if you remember, we said these carboxylic acids are actually named from the alkanes. Alkanes are the parent organic compounds. So the naming of all organic compounds originate from the alkanes. Whereby the alkane molecule, if you have methane, when you are naming these compounds, you only need to replace this E, that E over here. This E is replaced with the word oic, and then you add the word acid. Meaning that the first member of this group, you will have methanoic acid. That is the first member. Now, the second member of the alkanes is ethane, so you'll have ethanoic acid. The third member is propane, that is the alkane, so you'll have propanoic acid. And then you have the fourth member, which is butane, butanoic acid, and so on and so forth. These are the straight chain carboxylic acids, whereby this one will be the methanoic acid, or OH. You'll have CH3, COOH, CH3, CH2, COOH, that is propanoic acid, butanoic acid, OOH, and so on and so forth. So we said, you remember that if you have other substituents, like branches or other functional group, the carboxylic acid always takes the priority. Give an example of a molecule like this. If you have CH3, CH, you have bromine, COOH. So it means when you're naming this, it contains a bromine atom. this bromine atom, always take note of this, that this one is always carbon number 1, carbon number 2, and number 2, number 3. So this one will be 2-bromo-propanoic acid, 2-bromo-propanoic acid. Or you may have something like this, CH3, CH, have CH3, COOH, similar to this. So as I said, always make sure that this is carbon number 1, carbon number 2, and this is carbon number 3. So it means that this methyl group over here, this methyl group over here is attached on carbon number 2, and that means it becomes 2-methyl propanoic acid, 2-methyl propanoic acid. We can have another example, which is like this, CH3, CH3, bromine, COOH. So you have 2 substituents this time. You have an alkyl group and you have a bromine. So as usual, don't forget to count the longest, to locate the longest chain, number 2, number 3. So you have a bromine attached on carbon number 2, and you have the methyl also attached on carbon number 2 of the longest chain of this propanoic acid. So these 2 substituents have to be put in the alphabetical order. So it becomes 2, the methyl and bromo. So the B comes before M in the alphabetical order. So it will be 2-bromo, 2-methyl propanoic acid. Propanoic acid. We can have another example, another simple example. CH3, CHOH, COOH, CH3. So you still have, you're having the hydroxyl group, and then you have the methyl group. As we said earlier, make sure you have the longest chain, but always this carbon that contains the carboxyl group is always carbon number 1. So you have the methyl, and you have the hydroxyl, and you have the methyl. Those are the substituents attached on the longest chain. Alphabetical order again. So this will be the hydroxyl and the methyl, which comes first. Of course, it is the hydroxyl. So you'll start with 2-hydroxy, 2-hydroxy, 2-methyl, 2-methyl propanoic acid. And then we mentioned even some other isomerism. We said mainly these carboxylic acids, the carboxylic acids, their chain isomers exist, or chain isomerism, or you may have even the functional isomerism and optical. So in carboxylic acids, we talked about the chain isomerism that exists. We talked about the functional isomerism, and then we mentioned again on the optical isomers, optical isomerism, the enantiomers, non-superimposable images. So that is what we mentioned in the previous lesson. So today we will be looking at the physical properties, and then we see how the acidity of these compounds vary within different compound of the carboxylic acids. So among the carboxylic acids, they are colorless liquids, with a disagreeable order. A disagreeable order, some of these compounds, especially the carboxylic acids with carbon number 5 to number 10, we describe it as a Gote order, but if you have ever tasted on cheese, you know the taste of the cheese. When you're tasting the cheese, that is some of the taste for the carboxylic acids. That is the smell. And these acids are produced by the skin of the carboxylic. In most cases, if you enter into the store room, a store which has been closed for some time, when you enter, there is a certain smell that comes. That smell is coming because of the carboxylic acids that are produced by the certain bacteria. Then the carbon atoms, more than 10, those carboxylic acids with more than 10 carbon atoms, they are waxy solids. And that order diminishes when they are solids. For example, like benzoic acid, even benzoic acid, it's not an aliphatic acid, it's an aromatic, but it doesn't have the same smell as that one of the carboxylic acid, of the aliphatic carboxylic acids. Talking about the melting points, these carboxylic acids have got polar and non-polar molecules. So it has got different types of parts of the molecule. For example, if you look at this R, the R we said represents a hydrogen or an atom, a hydrogen or alkyl group. Now, if R represents an alkyl group, then that means this one becomes, this bond here is polar. This is a non-polar part, and this is another polar molecule. So this is the non-polar, and this is the polar part. So it has got two parts. So because of the polar part, it can be able to form this hydrogen and this oxygen more electronegative, so it can be able to form the hydrogen bonds. So if it forms the hydrogen bonds, or they associate together, different molecules can associate together to form the hydrogen bonds, and that will increase the boiling point and the melting point. Let's take an example and compare these carboxylic acids with other molecules, especially the alkanes, of almost the same number of carbon atoms. Methanoic acid, it has the molar mass of 47, and propanoic acid has the molar mass of 44. But when you look at the boiling point, there is a very big difference, 8 and negative 190. Look at the boiling point. Methanoic acid boils at 100.5 degrees, whereas propanoic acid boils at negative 4.2. This is a gas, this is a liquid. Even look at the ethanoic acid with the molar mass of 60 and butane with the molar mass of 58. They are very close together. But when you look at their boiling points, look at the difference. 118, that is ethanoic acid, and negative 0.5. And yet they have almost the same molecular mass. Why is that one happening? It is because of the hydrogen bonds that are formed between the carboxylic acids and between the carboxylic acids themselves, and makes those hydrogen bonds are more stronger. They associate together to form what we call dimers. This is an example of the molecule of the dimer that is formed. So this hydrogen here forms the hydrogen bond. So you'll have another molecule. This is another carboxylic acid. So there will be a hydrogen bond formed over here. So you have the hydrogen bond formed here and another hydrogen bond formed over there, and two molecules associating together. Now, if the molecules associate together, they will form what we call a dimer. They form what we call a dimer. So dimers are molecules. A dimer is formed as a result of two molecules coming together to form a bigger molecule. I just remind you of one of the dimers that is very common. The aluminum chloride forms dimer. And you remember the dimer for this compound, where we said these molecules, they associate in this form. So this is aluminum, two aluminum chloride molecules associating together to form a dimer. So these are two molecules. They are associated together. This dimer here is associated through the dative covalent bond, but this one is through the hydrogen bonding. So the association of the molecules increases the boiling point because the forces, the energy that is required to break these bonds will also increase, because this one is positive, this is negative. So you'll have positive here, negative, so the association takes place. So because of that, that's why the boiling points keep on increasing. So solubility in water. Because of the hydrogen bonding, as I've said, these molecules are very soluble in water. So they can be able to associate with water molecules through hydrogen bonding. So if they associate through hydrogen bonding, therefore those molecules are able to dissolve in water. A simple example of how we can just show how the association takes place within these molecules. We may have, this is a carboxylic acid. So this is the hydrogen. So it means a hydrogen bond over here can also be formed. Then you have oxygen and hydrogen, something like this. So it forms because water is polar. Therefore, it can form the hydrogen bonds with water. So this hydrogen bond, molecules that can be able to form hydrogen bonds with water, they are said to be soluble in water. So this one can as well form the hydrogen bonds over here with another water molecule. This is another water molecule. So we may have the hydrogen. This is oxygen, the hydrogens over there. So here, there will be so many associations. Even another carboxylic acid. For example, over here, you may have another carboxylic acid associating. This is the oxygen. Now you have the hydrogen. This is carbon. You have oxygen and hydrogen. So this is another carboxylic acid. So this one can also associate with another water molecule. You may have another water molecule being associated. So many hydrogen bonds within the molecule can be formed, and molecules that can be able to form hydrogen bonds are soluble in water. Acidity of these carboxylic acids. So when we're talking about the acidity, you remember this is how the molecule can be able to release the hydrogen ions. So they, like other acids, of course, they will be, they turn litmus paper blue or red. They'll be able to react with the acid, react with bases, react with carboxylic acids. They are bitter and so on. So they have all the physical properties of carboxylic acid, of other acids. But Carboxylic acids, organic carboxylic acids are weaker acids. They are weaker acids, and their acidity even depends on other substituents. For example, if you have an acid, if you have such an acid, when it reacts with water, then it ionizes. The ionization, weak acids they partially ionize. So that is why we are using partial ionization. So it will form the ethanoate, the carboxylate ions plus the hydroxonium ions in solution. Or we can represent this as RCOH, aqueous, with the reversible arrows indicating carboxylate ions and the hydrogen ions, as simple as that. So they are weak acids, but to what extent are they all very weak? Do they have the same acidity? So the acidity of these compounds also depend on the substituents that are attached on this carbon that contains the hydrogen to be released. So if you look at this, as we mentioned in the previous lesson, when these substances ionize, for example, if we have this R, let's have a specific carboxylic acid ionizing to form the hydrogen ions and the ethanoate ions. So when they ionize, assuming we have another methanoic acid also ionizing to form methanoate ions. So which of these ones may release more hydrogen atom? When we're talking about the acidity, we refer to what extent will this bond here break to release the hydrogen ions. So when we're comparing these two, for example, which of these one is more stronger? You will have to look at this. When you look at the methyl group has got what we call positive inductive effect. Positive inductive effect. So with this positive inductive effect is that when you have the methyl group attached on this carbon that contains, so this methyl group donates, so it is always donating the electrons towards this carbon. So the electron density or the electron movement increases. That means it makes this one more stronger. This oxygen, hydrogen becomes more stronger compared to when you have the methanoate. The hydrogen ions have no effect. So that means this hydrogen here can easily break compared to this where the electrons are entering. So we have, this is positive inductive effect. And the bigger the alkyl group, the stronger the inductive effect and the weaker the acid. Meaning that if we have CH3CH2, COOH, it means this is propanoic acid. It is a weaker acid compared to ethanoic acid because of this big alkyl group. Assuming, for example, instead of having one of the hydrogen atoms is substituted by the chlorine, what would happen to this? So chlorine or any other electron withdrawing atom like chlorine, this chlorine has got what we call negative inductive effect. Negative inductive effect. So it has the ability to withdraw the electrons, and therefore that will weaken the bond. So the bond here becomes weak. And if it becomes weak, it means that this bond can easily break. So the bond can easily break. That means the chloroethanoic acid will be even a more strong acid than ethanoic acid and the methanoic acid because of the presence of this. What if you have a fluorine? Maybe CH2COO. What do you expect? Fluorine is more electronegative than chlorine. So that ability of pulling the electrons towards itself increases. And therefore, this one make this one to be a more stronger acid than the chloroethanoic acid. So finally, as we come to the end, I just would like to leave one simple exercise. Please capture the exercise and try the exercise and see whether you can be able to answer. Explain the reasons of the following observations. Propanoic acid releases more hydrogen ions in solution than 2-methyl propanoic acid. So here you'll have to use the inductive effect and the negative, negative and inductive effects to explain this. Fluoroethanoic acid is a stronger acid than ethanoic acid. So I've just mentioned that. Consider the molecules in the following table. Analyze them and rank the following acids according to the increasing order of the acidity. So you'll have strength as 1, 2, 3. Give reasons for your answer. So after the table, so you rank them. The stronger one, you'll give it number 1. Then the next following it, you give it number 2, and so on. So after ranking them in that order, please give a reason for why you have ranked them in that order. Thank you so much for this lesson. We will be together, I hope, in the next lesson, and have a good day. See you there in the next lesson.